After finishing the exponential ones, we will need these inverse functions and one-to-one function composition functions, so we can define the inverse functions of the exponential functions. By the way, what are the inverses of the exponential functions? Logarithmic. So that's what we'll discuss later today. Well, there's really not that much to say about exponential functions. What do we have? We can have three possibilities. Well, this one, the one in the middle, is really not an exponential. It's actually a horizontal line. It's a linear function, and that's a special case. So we have a couple of cases. So the form of an exponential function, it's a function of this form in which the variable, it's the exponent this time. For power functions like the ones that we discussed before, as polynomials, we had x to a power, x to the second, x to the third, or even x to the rational, like x to the 1/2, x to the 3/2, etc. However, in this case, it's different. It's the base, it's not the variable. The base is a number, but the exponent, it's the variable. So, well, these functions, these exponential functions are commonly used to model growth and decay, and well, it's going to depend on how the function is presented. Just by looking at a very important piece of information, we will know whether this is growth or decay. So population growth or radioactive decay, for example, growth of bacteria. Yes, oh yeah. You can see this right. Oh, there's two of them. Much better? Okay, so it's the sign of the exponent is going to tell us whether the exponential function describes a growth or decay. Well, in this case, it is the negative. It's the negative exponent, the one that describes decay, and positive exponent, the one that describes growth. Well, in particular, whenever the base of the exponential, which by the way can be any number, well, except 0, because 0 to any power, well, that's just going to be 0. But in the particular case in which b equals to 1, that's just going to be 1 to the x power. And what's 1 to any power? Is it not always 1? Which is described by this horizontal line, y equals to 1? Okay, so that's pretty much the picture of how this looks like. Well, of course, we can always describe the transformations and shiftings of this type of functions. We have the graph of the function y equals to 1/2 e to the negative x minus 1. Okay, in order to draw the transformations of this function, I would do it one at a time. Of course, we can just use a graphing calculator well, what do we have here? -1 means shifting down. What about negative x? In the exponent. When we change the sign of the x's, what happens?
Over
the y-axis will serve as a mirror, right? So it's reflection about the y-axis. However, when we have a sign in front of the function, that flips it upside down, and that's reflection about the x-axis. And what is this 1/2 going to do on the function overall? Shrink by a factor of 1/2, right? Well, let's roadmap. So we're going to start with e to the x, e to the e to the negative x. Why not? We can do that one next. E to the 1/2 e to the negative x, and lastly the -1. So we're going to do one at a time, and let's start with Well, the e to the x function, okay, let's copy it from here. It has a positive exponent initially, and regardless of the base, whether you have e to the x, 5 to the x, 7 to the x, it doesn't matter. The y-intercept is always the same because that's going to be whatever that number to the 0 power, which happens to be 1. That's the y-intercept, 0, 1. All right? And by the way, this base with the letter E, it's a special number like pi, that is 3.14, 15, blah, blah, blah. This is a special number. This is Euler's number. The x for the exponential is 2.71, 82, I believe. The remaining digits, well, I don't know. But it's one of those irrational numbers, special numbers like pi. Okay, so let's start with that one. Number 1, we have 0, 1, which is our intercept here, right? So that's e to the x. E to the x. Okay, let's look at the first transformation of the graph. Well, again, what is the negative x in the exponent going to do again? Reflect about the y-axis. So I'm going to draw the same graph with the same intercept. However, in this case, in the other direction. In fact, even the negative sign from the definition, well, that's going to tell us that it's going to be a decaying graph this time, right? And then, well, let's do the multiplication by 1/2. What is that going to do again? Shrink, right? But shrink, more specifically, shrink vertically. All right. So this will be, okay, number 1, again, this is e to the negative x. Let's do the next transformation. That's okay, the same decaying graph in this case. If this was the point 0, 1, well, this time the function is going to go through the point 0, 1/2, because that's the shrinking, the vertical shrinking by a factor of 1/2. And there's one more transformation in this case. Let me. Nope. No, I needed the other form. Okay. Oops, too big. Okay. Okay, like this, and okay, last but not least, what is that -1 at the very end going to do? Shift it down. Now, there's one piece of information I didn't mention before. Okay, these exponential functions have this horizontal asymptote at y equals to 0. All right? So, well, when it comes to decay, you know, it's like you can always think of a decay in the bacteria population. So just think of when you're cleaning your room or you're cleaning your house. Can you really clean 100% of the bacteria? In fact, those cleaning products typically say, oh, cleans 99.99% of bacteria. So it's never killing 100%. So that's because of the asymptotic behavior of the decaying function in this case. So we get infinitely close to 0, but not actually to 0. So when we shift these functions down, okay, let's first label 1/2 e to the negative x. And the last transformation, the last shifting is a shift down. And that's it's going to be 1 unit down. All right, and that's going to be instead the point 0 -1/2. All right, 0 -1/2, and and in this case we will as well shift this asymptote, which I didn't draw here. Let me go back to draw it. I didn't do it because it actually overlaps exactly on on the x-axis, but it's there. Typically we don't write it, it's not necessary, but when it comes to shifting up and down, it's important to put that horizontal asymptote into the picture. So, so I mean, again, it's the same transformations, the same shiftings that we did with the other functions last time. All we do is just extend this to the exponential function. And well, there's really not much to say other than, well, we're going to go back to this when we do the calculus of them. So in the meantime, let's move on to today's topic. Here it is. Inverse and logarithmic functions. That's 1.5, and I believe this is the last section in the review. I think next week we will be starting with the actual calculus, starting with limits and all that. So we're going to review inverse functions and logarithmic functions. So before we define what an inverse function is, we need to define what a one-to-one function is. And well, because the definition is that a function is invertible if it's one-to-one. That is, what do we mean by a one-to-one function? It's a function that never takes the same output for different inputs. You know, if you think of a quadratic equation, the parabola, for example, we may get the value of y equals 4 for two different values of x, that is for positive 2 and negative 2. So in this case, it's not a one-to-one function. Alright? That is, the definition is that we don't get the same value of y or f of x for different values of x. That's the formal definition. And you might remember the horizontal line test. The horizontal line test is to test whether the graph of a given function is a one-to-one. The other one was the vertical line test, and that's just to determine whether it is a function. That is, if the vertical line only crosses the graph at only one point, well, it's a function. If it crosses more than 2 points, that's essentially saying that we're in two different places at the same time, which is not possible, so that's why that doesn't describe a function. The horizontal line test, on the other hand, yes, it's understood that we have to have the graph of a function, but that's to determine whether it's one-to-one, and therefore later will be invertible. So let's look at graphs of y equals x cubed and y equals x squared to determine which of them is one-to-one. So, and we're going to use in this case the graph, or rather the vertical line test. No, I mean the horizontal line test. So how does the graph of y equals x cubed look like from the parent graphs from the other day? So it's like an S, right? And it's always increasing, I think. Alright? Does that look about right for y equals x cubed? Alright, so let's trace some horizontal lines. How many times did it cross? Only once? Can you find a point for which it crosses more than once? No, so there's no way. So that means in this case, yes, one-to-one. Alright, what about the second function, y equals x squared? Well, we already discussed that one with values. Well, so that's the parabola. And in this case, well, let's trace horizontal lines. And what happens here? How many times does the horizontal line cross with the parabola? Twice, right? Twice. Well, even though we could argue that at the vertex crosses only once, that's true. I would agree with that. However, there's other places in the graph of this parabola where the horizontal line will cross more than once, and for that reason, not one-to-one. That's not going to be one-to-one. All right. Well, let's look at another definition, another kind of visual in connecting the one-to-one functions to inverse functions. So again, the idea is that really the theorem, the formal definition is that a function will have an inverse if and only if it is one-to-one, and vice versa. If it's one-to-one, then it is invertible. All right. So you can think of these invertible functions as recycling, you know. So we get I don't know, a drink, a soda, for example, or iced tea. What do we do with the can? Throw it away. That's our output. Well, then the recycling company takes that as the input and turns it into a clean can to use it again to drink the same tea, most likely, right? And that their output, it becomes our new input, isn't it? So that's like the recycling. That's like the one-to-one functions. That is. So here, let's go with the definition. So a given function has a domain A and a range B. And let's draw a picture for this. Okay, that's fine. So f of x. So if we input some x, we will output some y, right? But for the inverse function, the output of the original function is the inverse's input, and vice versa. The output of the inverse is the original function's input, right? So that's going to go over and over in circles. This idea is very important when it comes to define inverse functions of other functions that we're going to do soon. All right, so to illustrate this, if f is a one-to-one function with this value, so f of 1 equals to 5, f of 3 equals to 7, and f of 8 equals to 10. That is, in this case, these functions' values, we can interpret them as order pairs. However, I'm going to write these values in the notation of a mapping. So, where the first bubble right here will denote the domain and the range. That is, the domain is the inputs, the values inside of the parentheses, and the outputs are going to be the y values. Recall that when we see this notation like f of 1 equals to 5, what we're really seeing, what they're really telling us is that is the order pair 1, 5. All right, it's just function notation, fancier notation to say the same thing. Well, so I'm going to make a list of the x's, so that's 1, 3, and 8, and 5, 7, and negative 10. All right, so let's just draw the correspondence with arrows. All right. And in this case, well, this is a one-to-one function because, well, to begin with, this is a function because for every input, we have only one single output. If we had two different outputs for the same input, well, we're in trouble. We cannot be in two different places at the same time. However, this is also a one-to-one because there's no like two inputs going to the same output, like negative 2 on the parabola going to positive 4 and positive 2 going to also positive 4. In this case, we have that one-to-one correspondence. Now, given those points, well, they're asking us to find the inverse of 7, the inverse of 5, and the inverse of negative 10. In other words, let's draw the same bubbles here. No, not yet. Same bubbles. And 1, 3, 8, 5, what's that, a 7, and negative 10. So, they're asking us for the inverse function of 7. Well, so from the same order pairs, the number 3 took us to the number 7. The inverse process is telling us that the 7 is going to take us back to 3. Okay, so let's point that with an arrow here. So 7 goes back to 3. What is f inverse of 5? That's going to take us back to 1. And last but not least, f inverse of negative 10, well, goes back to 8, right? That's going back and forth between both sets. And let's label this as this is the range and this is the domain, because we start the range of the original function, which is the domain of the inverse function, and then that's how we're going to go back and forth between them. Right, so that's the picture using this mapping notation of functions, not really using the explicit expressions of x, which we will do, by the way. So number 1, okay, let's see. Okay, the algebraic implications here, that means when if recall this bubble symbol from last time, isn't that the composition function? So that means that when we do the composition of a function and its inverse and vice versa, we get that equal to x. Well, so this is something that you may have learned that you learn in high school, in intermediate algebra, or whatever math class that you took. And well, so if they just ask you to memorize these two formulas, well, we're gonna make more sense out of it about what this really means. But before having a look at this definition, how about we look at steps to finding the inverse function? Okay, and that's something that, of course, you did in pre-calculus, in intermediate algebra as well. So let's see. So in this case, well, we're going to work with a function that we know it's a one-to-one function, right? For example, if we have f of x equals x squared plus 2, for example, well, that's not going to be a function, rather, that's not going to be a one-to-one function unless we restrict the domain, which is a trick that we will do later. So in the meantime, let's work as an example with a function that has an inverse. Okay. Sometimes functions may be given using the f of x notation, the f notation, but in some cases they're going to give us the y notation. So if we're given the function using the f notation, replace that f of x with y. But in this case, again, it's given as y. So y equals x cubed plus 2. And, okay. Y equals x cubed plus 2. Isn't it the graph of x cubed shifted 2 units up? Yes? Which is actually the graph that we have here. Which of the two graphs, the red or the blue one? The red one, right? So let me highlight. And then I'm going to do the next. So the next step is to interchange the x's with the y. So that's actually inverting the function. So we reverse the order of the x's and the y's. So x equals to y cubed plus 2. And the next step, number 4, solve for y. Solve the equation for y to obtain a new function. And well, subtract 2 to both sides to get y cubed equals x minus 2. And to get y by itself, so we have y cubed. What do we do to get the y by itself, by the way?
Cube root.
Take the cube root on both sides, right? So y equals the cube root of x minus 2. Alright, we also look at the graph of the cube root. Well, actually, what was that, on Monday, I think, when we look at the parent graphs, we'll look at the graphs of radical functions of odd indices and radicals of even indices, right? Well, in this case, we have that of an odd index. So, in this case, well, this minus 2 from the shifting means that we shift the graph 2 units to the right, which pretty much it's represented by the other graph that we have in blue right here, isn't it? Alright, well, this is y, but in this case we need to use function notation. This y, because if we look at this, y equals x cubed plus 2 and y equals the cube root of x minus 2, well, those are just functions. But we need to be very specific which one is the original function and which one is the inverse function. So that's why the very last step is telling us to replace y with the inverse function notation. So all we do is f inverse of x equals to the cube root of x minus 2. Alright, geometrically, did you see how these two graphs have a symmetry? These graphs are symmetric about the line y equals to x. So you can think of this diagonal line y equals to x as the mirror of those two graphs, of the graph of a function and its inverse. Alright? Now, one quick note on notation. Be careful. This f to the negative 1, but actually it's not f to the negative 1. We don't read it f to the negative 1. We read it f inverse. This is not equal to 1 over f of x. I know, because we have this negative 1 power symbol at the top of the letter f, but no, that doesn't mean it's reciprocal. However, a function f of x to the negative 1, this is equal to finding its reciprocal. Alright, so the position of this negative 1 symbol matters. If it's right on top of the letter f, means inverse function, not reciprocal function. Okay? That being said, well, now that we discussed a little bit on inverse functions, invertible functions, and one-to-one functions, well, and connecting with what we did at the beginning with the exponential functions, we're ready to define the inverse functions of those exponential functions. Well, you already answered that question when I asked you, well, what was their inverse of an exponential function? And it's the logarithmic function. Well, so exponential functions have a base raised to a power x, not like the polynomials functions that have the x, the variable, as the base and raised to numerical values. In this case we have the exponential that have a base. Logarithmic functions also have a base, and if we were to define these functions as inverses to one another, it would be the same as saying the same base as this exponential function. For example, and well, the definition of an exponential function is the logarithm of x on the base a is the power y such that the base raised to the y value equals the same value. Well, right now in symbols, let's do some examples so this makes more sense. Okay, number one, the domain of the logarithm of the logarithmic function is 0 to infinity. We already discussed that on Monday when we reviewed all the parent graphs. Let's draw the graph again. So let's draw the graph of the logarithmic function. It looks like this. All right, and in comparison with the exponential function, so this is okay, let me call this ln of x for now, and let me compare this with e to the x. So the exponential function increases that way, and it has a horizontal asymptote. All right, just so we can see the differences between the function and its inverse. All right, there is this invisible or hard to see horizontal asymptote that we usually don't draw, but it's there. However, the logarithmic function goes to negative infinity, but without actually touching the 0, because, well, what's logarithm of 0? Isn't that undefined? I mean, if we evaluate the function, it's undefined. But when we find limits later next week, that's where the infinities are and the DNEs are going to be brought to the conversation. But in this case, well, if e to the x is this graph and has a horizontal asymptote, its inverse has to have an asymptote on the other direction. So it has a vertical asymptote for which we never touch that 0, because ln of 0 it's actually an undefined value. All right, now as opposed to exponential functions, well, we just call it exponential function, a to the x, 7 to the x, e to the x, even though e to the x is the natural exponential function because the base is a special number, e Euler's number. However, logarithms have two special presentations, and the number one special presentation is the natural logarithm. Natural logarithm function, which is the logarithm whose base is the number e. Well, why isn't the natural log NL instead of ln? Because, well, we're using the root that comes from the Latin language, Logarithmus naturalis, right? In that order for the initials of the name. So, you know, like many other words in mathematics come from, or rather inherit their Latin roots, like in analytic geometry. Focus, that's not an English word, that's actually a Latin word. What else? Focus, and it's plural, foci, you know, we use those letters, or rather those words. And well, what does that mean when we compare the logarithm with the exponential? So y equals ln if and only if x equals e to the y. The other important logarithm is the common logarithm. The common logarithm in which the base is the number 10. And you will recognize this logarithm when, well, let me scroll this down a little bit. Actually, let me rewrite this ln in a different way. Log base e of x. So in this case, we would recognize a common logarithm or a logarithm base 10 when we just see the word log without any subscript here. That's the common logarithm. Or otherwise, you would just see log base 2 of x, log base 3 of x, you know, other bases, right? But the most common ones that we will use are the common logarithms, base 10, and the natural logarithm. But I mean, a lot of words, a lot of symbols. Let's interpret this actually with actual numbers. Okay, when we see this expression, logarithm of 100, so we're asked ourselves, what power of 10 equals 100? Where am I getting this 10 from again? Isn't that this implied subscript? We don't need to write that implied. If you want to write it, that's fine. But we don't need to write that one, okay? So that's the question. What power of 10 equals 100? 2, okay? Now, let's rewrite this in its corresponding exponential form. So, logarithm of 100 equals to 2 because 10 to the second power equals 100. That's the definition of going back and forth between exponential form and logarithmic form. Let's write the next one. Any ideas? Logarithm base 4 of 16. We ask ourselves, what power of 4 equals to 16? Also 2, right? And that's because 16 equals 4 to the second power. This is how we go back and forth between logarithmic version and exponential version. So, and in general, when we have a logarithm of x on a base e equals to y, we ask ourselves, what power what power of a rather equals x. All right, that's how we go back and forth between the two notations. Okay, of course, I mean we could go on forever and forever, but I mean I think these numerical examples, hopefully this makes sense about how do we go back and forth between the two. Let's see. More stuff that you learn in pre-calculus, it's the properties of logarithms. We have the product rule, the quotient rule, the power rule. I have a special name for the power rule. I will show it to you in a minute. And then we have the inverse properties. And these inverse properties are the ones that we use to solve exponential and logarithmic equations. And I'm going to give you one example when I get to those. For example, Let's see the product rule in action. So for example, when we have let me just do log base 7. I mean, any base is fine. Log base 7 of 5x. Using the product rule, because we have a product in the argument is the expression inside of the expression inside of the logarithmic function. And, well, by the product rule, that's log base 7 of 5 plus log of x. In other words, we write the product of the logarithm of a product into the sum of two logarithms. The quotient rule. So this time I'm going to use ln. ln of 6 over y. Well, the quotient is written as a difference. In this case, ln of 6 minus ln of y. A very important property of logarithms is that power rule. Question?
On the first, the product rule equation, shouldn't it be log base 7?
Oh, yeah, base 7. Thank you. Yes, thank you. Log base 7 of x. Thanks. All right, the power rule. And actually, let me make this smaller to make more space. So let me write it down here. So in this case, well, this one has a special name. I call this the basketball rule, the basketball smackdown rule. Why? Well, so if we use this rule in this direction, what are we doing? This r is becoming a power, isn't it? This coefficient becomes a power like basketball, right? In this direction it's basketball. And in the other direction, it's the power jumping in the front as a coefficient that's smackdown. All right, so that's a very important property that we were going to use a lot when we get to differentiating logarithmic functions and to perform logarithmic differentiation. Two different things, but highly related. You'll see when we get there. As an example, very brief example. I mean, let's use log, just a common log of y to the 7th power, so that's just going to be 7 times log of y. There's really nothing crazy to do about this. Of course, when we have like an example in which we combine more than one rule. Question?
If there is no base, do we have to consider it as 10?
Yes, it's base. It should be understood that it is a base 10. Just like radicals, you know, when we have the square root of x, unless we have a 3, a 4, or a 5, well, when we don't have any number here, it's implied to be the square root in a similar way. All right, inverse properties between logarithms and exponentials. So essentially, the logarithm of the same base as the exponential cancel out to each other, all right, and leave us with x. Likewise, a raised to a logarithm of the same base cancel each other and outputs the x. But we need to be very careful, because in this case, for the first property, this is for x can be any real number, all right? Because we have the exponential function, and the exponential function doesn't have any restrictions. However, the other inverse property, notice that we would be inputting an x in a logarithmic function. Will the logarithmic function accept any number as an input, or does it have any restrictions? Can we plug in? Can we evaluate logarithm of a negative number? Can we evaluate logarithm of 0? That's also undefined, right? So in this case, x only can be greater than 0. Well, let me tell you something. Throughout your life in mathematics, they have told you that that the logarithm of a negative number, it cannot be evaluated. But if any of you are math majors, you're going to see about that in complex analysis. Electrical engineers, you will see how to find. You will use complex variables, complex analysis a lot, in which you will evaluate logarithms of negative numbers. You'll see how fun those are going to be. Question?
Like log of negative number are very small numbers, but still possible.
Yeah, so it has some implication. It's actually like an equation with infinity. In fact, the logarithm of a negative number, it's actually infinitely many values. It's weird. You'll see that in complex analysis. All right, guys. So let's see what's next. Where we still have a few more minutes. So to illustrate these inverse properties, let me make up an example of an exponential equation real quick. So e to the 2x plus 5 equals to 10. So we want to solve for x. We want to get rid of the exponential. How do we cancel the exponential? Any ideas? Yes. Have the natural log, alright? Take natural log on both sides. And then, well, in this case, these two cancel. And we will be left with 2x plus 5 equals ln of 10. And well, solving for x, this is 2x equals ln of 10 minus 5. And x equals 1/2 ln of 10 minus 5. So this is how we use the inverse properties to solve exponential equations. Now let me change the equation, just make it slightly different. What if we had instead 7 to the 2x plus 5 equals to 10? Okay, someone else give me an answer how to solve, what to do first. Yes.
Natural, or the log of 7.
In this case, not the natural log, because the natural log is a logarithm on a base e. That's why it works in this case. So in this case, we need to do a logarithm on both sides on a base 7. This way we can cancel these two, and we will be working on a logarithm on a base 7. Alright guys, so the next topic is to define the graphs of the inverse function, the inverse trigonometric functions. But well, I really don't want to rush through this, so I'll let you go a few minutes or